Welcome to your complete Q&A guide for the WGU Data-Driven Decision-Making exam. No simple answer revealed. We test you with real exam-style questions and explain the full logic behind each choice. In this session on Domain 1, Foundations of Quantitative Analysis, will cover the definition and value of analytics, the three types of analytics, applications and big data, the three-stage analytics model, the 4 levels of measurement, just a reminder. Our website offers free study guides and practice questions designed to help you pass your C207 exam with confidence. You'll find the link right in the description below, so be sure to check it out and start studying smarter, not harder today. Alright, let's dive in. Question 1. A regional logistics company has spent 3 years collecting detailed records of every delivery, fuel purchase, and driver shift, storing all of it because cheap cloud storage made keeping everything easy. Leadership notices that despite this huge archive, the company still makes routing and staffing decisions by gut feel, and the stored records have never improved a single decision. Which idea best explains why the raw archive has produced no value so far? Your options are: A. The company has collected too little data to support any meaningful conclusions. B. A large set of data has little value until it is described and analyzed with statistics. C. Cheap storage and processing power have made data collection economically impossible. D. Quantitative analysis applies only to financial data, not to logistics records. Which one is it? Pause the video if you need more time. The correct answer is B. A large set of data has little value until it is described and analyzed with statistics. B is correct because the course stresses that data is raw material, and a large set of data by itself is not valuable until it can be described and analyzed. Statistics is the toolkit that converts the stored archive into usable conclusions, which is exactly the step this company has skipped. A is wrong because the scenario describes a huge 3-year archive, so scarcity of data is not the problem. The course's point is that abundant data still needs analysis, not that more raw records would help. C is wrong because cheap storage and processing are what made the large archive possible in the first place, so they enable collection rather than prevent it. The course presents low cost as the reason data has become abundant. D is wrong because quantitative analysis applies across business, healthcare, military, government, and many other settings, including logistics operations like routing and staffing. Limiting it to finance contradicts the course's wide view of analytics. Quantitative analysis is the discipline of turning raw evidence into decisions, and it leans on statistics to do it. Its core idea is simple: a pile of untouched data carries almost no value on its own. A warehouse stacked with unexamined customer records is no more useful to a company than a warehouse of unread books is to a reader. Value only appears once someone summarizes the data and draws inferences from it. Storage and computing have become remarkably cheap, so organizations now keep nearly everything instead of throwing most of it away. But that abundance only pays off when it's paired with analysis. Cheap data without analysis is just clutter, and analysis without data has nothing to work on. Picture a delivery company that has recorded every shipment, fuel purchase, and driver shift for years. Until someone describes those patterns and analyzes them, the archive is just potential energy that has never been converted into a better route or staffing decision. Having a mountain of records doesn't make an organization data-driven. Only summarizing and analyzing that data does. Remember, data is raw material, useless until someone refines it into something a decision maker can actually use. Question 2. A hospital reviews its surgical complication rates and compares them against the national average and against peer hospitals, partly because an accreditation organization requires this information on a regular basis. Which point does this scenario best illustrate about analytical decision-making in organizations? Your options are: A. Hospitals should analyze outcomes only when a surgeon requests a personal performance review. B. Comparing outcomes to a national average is descriptive of the past and therefore cannot inform decisions. C. Healthcare is one of the few fields where benchmarking against competitors is prohibited. D. Some analysis is driven by external requirements, so it must be performed routinely rather than occasionally. Take a second. Which answer would you pick? The correct answer is D. Some analysis is driven by external requirements, so it must be performed routinely rather than occasionally. D is correct because the course uses this hospital example to show that accreditation organizations require outcome data regularly. So the analysis is driven by an external requirement rather than internal curiosity. That external driver is why the hospital must perform the analysis routinely instead of only now and then. A is wrong because the analysis here serves institutional benchmarking and accreditation, not a single surgeon's request. The course frames it as an organization-level recurring obligation. B is wrong because comparing outcomes against benchmarks directly supports decisions about where care can improve. So describing the past is the starting point for action, not a dead end. The course treats benchmarking as decision relevant. C is wrong because the scenario shows the hospital comparing itself to peer hospitals and the national average, which is benchmarking, not a prohibited activity. The course presents this comparison as expected practice. Organizations face countless decisions, and one useful habit is asking which ones can be studied with data instead of instinct. The test is simple. If a measurable outcome exists, that decision can be analyzed. Hospitals illustrate this perfectly. They pull data from their own patient records on surgical outcomes, then compare those results against other hospitals and the national average. A process called benchmarking. Accreditation organizations require hospitals to report outcomes on a regular schedule. This external mandate makes the analysis continuous rather than optional, unlike analysis driven only by internal curiosity, which tends to be a one-time study. The same pattern shows up everywhere. Retailers study shopping trends to forecast sales and promote products. A university baseball team might track home field performance late in games. Each case starts with a measurable outcome and a specific answerable question. Watch for scenarios mentioning accreditation, regulation, or mandated reporting. That's the signal that analysis must be repeated on a steady cadence, driven by an outside requirement rather than internal curiosity alone. Question 3. A management consultant is asked to give the precise definition of analytics adopted by the course, attributed to Thomas Davenport and Davenport-Kim. Which statement matches that definition? Your options are A. The extensive use of data, statistical and quantitative analysis, explanatory and predictive models, and fact-based management to drive decisions and add value. B. The collection and indefinite storage of as much organizational data as possible for unspecified future use. C. The process of discovering hidden patterns within very large databases through automated search. D. The use of spreadsheets and relational databases to keep organizational records neatly organized. Before I reveal it, which one do you think is right? The correct answer is A. The extensive use of data, statistical and quantitative analysis, explanatory and predictive models, and fact-based management to drive decisions and add value. A is correct because this is the exact Davenport and Kim definition the course tells students to memorize, emphasizing extensive data use, rigorous analysis, explanatory and predictive models, and fact-based management aimed at driving decisions and adding value. Each phrase carries weight, and the closing purpose is better decisions that create value. B is wrong because hoarding data for unspecified future use describes mere collection, which the course explicitly contrasts with analytics. Data has no value until it is described and analyzed. C is wrong because discovering patterns in large databases describes data mining, a related but distinct concept. Analytics is the broader fact-based management practice, not the pattern search step alone. D is wrong because storing records in spreadsheets or databases is data organization, a data management activity. It is a preparatory step, not the definition of analytics. Analytics has a precise, authoritative definition from Thomas Davenport and Kim that every professional should know word for word. Let's break down exactly what it means. Every phrase here carries real weight. Extensive use of data means sustained, repeated analysis, not a single glance at a dashboard. Statistical and quantitative analysis means rigorous math, not gut feeling. And fact-based management means letting evidence, not authority or intuition, settle decisions. Explanatory models account for what is happening and why, while predictive models project what is likely to happen next. Genuine analytics does both, and it all exists for one practical purpose: to drive decisions and add value. Don't confuse analytics with its neighbors. Mere data collection adds nothing without analysis. Data mining is just pattern discovery, and data management is just neat storage. Analytics is the broad fact-based practice that uses all of these pieces together to drive decisions. The single most important benefit this definition captures is that analytics lets an organization make decisions based on hard information rather than guesswork. Question 4. A company's leadership already uses big data to predict market trends and analyze customers, but now wants to apply analytics to its own workforce. According to the course, which of the following is an example of this inward-facing use of analytics? Your options are: A. Estimating future quarterly sales from historical shopping trends. B. Promoting products similar to a customer's prior purchases through targeted email. C. Improving hiring practices, increasing employee retention, and analyzing compensation. D. Comparing surgical outcomes against an industry benchmark for accreditation. What's your answer? Commit to one before I continue. The correct answer is C. Improving hiring practices, increasing employee retention, and analyzing compensation. C is correct because the course explicitly states that management may use big data internally to improve hiring practices, increase employee retention, analyze compensation, and develop top talent. These are inward-facing decisions about people and pay, exactly what the scenario asks for. A is wrong because estimating future sales from historical trends is an outward-facing retail decision about the market. It analyzes customers and demand, not the company's own workforce. B is wrong because promoting similar products to past buyers is outward-facing customer marketing. It targets consumers rather than internal talent or compensation. D is wrong because benchmarking surgical outcomes is an outward-facing comparison against other institutions for accreditation. It concerns clinical quality, not internal human resources decisions. Business analytics isn't just about customers and markets. The same analytical mindset applies inward, toward a company's own workforce, and those uses are easy to overlook. Management can use big data to improve hiring, increase retention, analyze compensation, and develop top talent. Each is a people decision, but each produces measurable outcomes that analysis can illuminate. Predicting which customers will buy and predicting which employees will leave are mechanically the same kind of work. Take historical data. Find attributes that forecast an outcome and act on that forecast. Only the topic changes, the method stays the same. The military version makes this vivid. Measuring equipment quality, evaluating recruiting, predicting deployment, and calculating supplies are really quality control, marketing, workforce planning, and supply chain management wearing a uniform. Turnover, performance scores, and pay figures are all measurable, so hiring and talent decisions are analytics too, not just sales forecast. Recognizing that lets a company apply its analytical skill everywhere, not just in marketing. Question 5. A military planning unit uses simulations based on past engagements to estimate how many casualties might be taken in an upcoming battle. Within the course's discussion of how analytics is used across settings, this specific use is best categorized as which kind of analytical work. Your options are A. Supply chain management because it helps determine how many rations and weapons are needed. B. Research that predicts a future outcome by drawing on historical engagement data. C. Marketing analytics because it evaluates which recruits are most likely to enlist. D. Equipment quality measurement because it assesses vehicles, weapons, and body armor. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is B. Research that predicts a future outcome by drawing on historical engagement data. B is correct because the course lists predicting battle casualties from simulations of past engagements under research, and structurally it is predictive analytics because it uses historical data to project a future result. The life and death stakes do not change the underlying method. A is wrong because supply chain management in the course covers calculating needed rations, equipment, weapons, and troop counts, not forecasting casualties. Those are logistics quantities, not a predicted battle outcome. C is wrong because marketing analytics in the military example evaluates recruiting strategies and predicts likely recruits. That mirrors consumer prediction, which is a different application than estimating casualties. D is wrong because measuring equipment quality assesses vehicles, weapons, and body armor. That is a manufacturing style quality function, unrelated to forecasting how many soldiers might be lost. The military example does double duty. It shows how analytics spreads across every function of a large organization, and it shows predictive analytic applied to the highest possible stakes. A military can measure equipment quality, test new weapons and training, predict which recruits will succeed, forecast deployments, and calculate rations and supplies for a mission. Each of these mirrors an ordinary business function, from quality control to workforce planning to supply chain management. Consider one striking case. A planning unit predicts casualties in a coming battle by simulating past engagements. Historical data projects a future outcome. That is the entire machinery of prediction, no matter how grave the subject. Classification depends on the structure of the work, not on how much is at stake. Forecasting casualties from prior battles and forecasting revenue from prior quarters both take history and extend it forward. Gates says the difference lies only in the domain. Without quantitative analytics, high-stakes decisions rest on instinct instead of hard data and carry a greater chance of failure. Analytics offers no certainty, but it offers a meaningfully better chance of getting the decision right. Question 6. A retail analyst is asked only to summarize what happened to sales during the previous quarter, with no projection or recommendation attached. According to the course's three-way classification of analytics, which type is the analyst performing? Your options are A. Descriptive analytics, which summarizes what has happened using past data. B. Predictive analytics, which projects past trends forward into the future. C. Prescriptive analytics, which recommends an action to take. D. Optimization, which finds the best balance between two competing variables. Which would you go with? Lock it in before the reveal. The correct answer is A. Descriptive analytics, which summarizes what has happened using past data. A is correct because descriptive analytics describes or summarizes what has already happened, and it relies on past data, which is precisely the task of reporting last quarter's sales. The analyst is asked only to summarize with no forecast or recommendation. B is wrong because predictive analytics would project the trend forward to estimate a future quarter. The scenario explicitly excludes any projection. C is wrong because prescriptive analytics would recommend an action to influence the outcome. No recommendation is requested here. D is wrong because optimization is a prescriptive technique that maximizes one variable relative to another. Summarizing past sales involves no such balancing of variables. Analytics splits into three types based on what the work aims to do, and descriptive analytics is the first. It summarizes what has already happened, turning past data into a clear picture of an organization's recent reality. Every defining question it answers looks backward at events that have already concluded, like sales last quarter, customer losses last month, or which region shipped the most units. This comes first because an organization can't reason about the future until it has an honest picture of its present and past. If you can't accurately state last quarter's revenue, you have no reliable basis for predicting or improving next quarters. The data feeding descriptive analytics is always past data, and the output is only a summary. The moment someone forecasts next quarter, it becomes prediction. The moment someone recommends a price change, it becomes prescription. Descriptive analytics isn't trivial. A flawed summary poisons every decision and forecast built on it. The simplest test: if the data looks backward and the result is just a summary, with no projection or recommendation, you're looking at descriptive analytics. Question 7. A subscription streaming service uses 2 years of viewing history to estimate how many hours customers will stream next month. No specific action or recommendation is produced. The output is simply a forecast. Which type of analytics is this? Your options are A. Descriptive analytics, B. Prescriptive analytics, C. Optimization, D. Predictive analytics. Don't overthink it. Which one feels right? The correct answer is D. Predictive analytics. D is correct because predictive analytics uses past data to project trends into the future, which is exactly what forecasting next month's streaming hours from 2 years of history does. The output is a forward-looking estimate rather than a recommendation. A is wrong because descriptive analytics would summarize what streaming looked like in the past, not estimate a future month. The scenario produces a forecast which goes beyond description. B is wrong because prescriptive analytics would recommend an action to change the outcome. Here the service only forecasts and prescribes nothing. C is wrong because optimization is a prescriptive technique that balances competing variables to recommend a best action. No variable is being maximized or minimized in this forecast. Predictive analytics takes the summary that description provides and extends it into the future, using past data to project trends forward and estimate what is likely to happen next. Predictive questions always sound like this. What will sales be next quarter? How many customers are likely to cancel? Or which shipments will probably run late? Each one reaches toward an outcome that has not yet arrived. The mechanism rests on a simple assumption. Patterns observed in the past tend to continue. So history contains clues about what comes next. A streaming service that has watched 2 years of viewing behavior can estimate next month's hours streamed, because the forecast is built entirely from past data, even though the thing it forecasts hasn't happened yet. Predictive analytics still relies on past data, exactly like description, but it presses further by fitting a trend and projecting it forward. What it deliberately does not do is recommend an action. It forecasts an outcome, but stays silent on how to respond, since that step belongs to prescription. For study purposes, ask two things. Is the work oriented toward the future? And is the output a forecast rather than a recommendation? If both are true and no action is advised, you're looking at predictive analytics. Question 8. After forecasting that sales will dip next quarter, a company asks its analytics team not just for the forecast, but for a specific recommendation on what pricing and inventory actions would keep revenue stable. The team draws on current conditions and projected future data to suggest a course of action. Which type of analytics does this represent? Your options are A. Descriptive analytics because it reports on a coming quarter. B. Predictive analytics because a forecast is involved. C. Prescriptive analytics because it uses current and projected data to recommend actions. D. Data mining because it searches a database for patterns. Got a guess? Lock it in. The correct answer is C. Prescriptive analytics because it uses current and projected data to recommend actions. C is correct because prescriptive analytics is distinguished by its ability to use current and future projected data to make suggestions and help direct decisions. Recommending specific pricing and inventory actions to protect revenue is exactly that recommend an action step. A is wrong because descriptive analytics only summarizes what has happened and would not generate a recommended course of action. The scenario goes well beyond reporting. B is wrong because a forecast alone is predictive, but the task here adds an explicit recommendation about what to do. The recommendation is what pushes it into prescriptive territory. D is wrong because data mining discovers patterns in large data sets and does not, by itself, prescribe actions. The defining feature here is the action recommendation, not pattern discovery. Prescriptive analytics is the third and most ambitious type of analytics, and one feature sets it apart from the other two. It recommends an action. Descriptive analytics summarizes what happened, and predictive analytics forecast what will happen. Prescriptive analytics goes further, advising what the organization should do to influence the outcome. A concrete example makes this click. A company reports revenue fell last quarter. That's description. It forecasts revenue will fall again. That's prediction. Then it recommends cutting price by a specific amount now. That's prescription, because it issues an instruction rather than just stating facts. Unlike description and prediction, which lean on past data, prescriptive analytics folds in current and projected data to reason about consequences before they happen. Because a bad recommendation steers real decisions, it depends on sound description and prediction underneath, and its sharpest form is optimization, computing the single best course of action. The test is simple. If the analysis tells the organization what to do, it's prescriptive. If it only summarizes or forecasts, it's one of the other two. Question 9. A manufacturer builds a model to find the minimum amount of labor needed to achieve the highest possible factory output, pushing output up while pushing labor costs down. Which analytics concept does this model exemplify? Your options are A. Optimization, a prescriptive technique that maximizes one variable in relation to another. B. Descriptive analytics that summarizes historical labor costs. C. Reliability testing of the production data. D. A prospective cohort study of factory workers. Which one is it? Pause the video if you need more time. The correct answer is A. Optimization, a prescriptive technique that maximizes one variable in relation to another. A is correct because optimization is the course's textbook prescriptive technique, defined as seeking to maximize a certain variable in relation to another. The model simultaneously raises output and lowers labor costs and then recommends the exact labor level to use, which is a prescriptive action. B is wrong because summarizing historical labor costs would be descriptive analytics. The model here recommends an optimal action rather than describing the past. C is wrong because reliability concerns whether a measurement is consistent and repeatable, which is unrelated to balancing output against labor. The scenario is about finding a best operating point, not testing measurement stability. D is wrong because a prospective cohort study is an observational research design that follows a group forward in time. It has nothing to do with maximizing factory output. Optimization is the textbook example of prescriptive analytics. It doesn't just describe or predict, it calculates the best possible action to take. Picture a factory manager who wants maximum output with minimum labor cost. Since more output usually needs more labor, these goals pull against each other, and optimization finds the exact point that satisfies both as well as possible. Every optimization problem has the same shape, an objective to maximize or minimize, variables that can be adjusted, and constraints that limit the possible solutions. The model searches all combinations and returns the one that best serves the objective. Describing past output is descriptive. Forecasting next month's output is predictive. But computing the exact labor level that yields the best output and telling the factory to use it is prescriptive, because it issues a directive. The classification isn't about whether math or data is involved. Every type uses those. It's about purpose. Optimization exists to recommend the best action, and that's what makes it prescriptive. Question 10. Two analysts present findings. The first says their model shows sales will fall about 5% next quarter. The second says their model recommends cutting price by 3% now to keep sales flat. Which statement correctly classifies the two analysts' outputs? Your options are: A. Both are predictive because both rely on a model. B. The first is predictive and the second is prescriptive. C. The first is prescriptive and the second is predictive. D. Both are descriptive because both summarize the data. Take a second. Which answer would you pick? The correct answer is B. The first is predictive and the second is prescriptive. B is correct because predictive analytics forecasts what will happen, which is the first analyst's claim that sales will fall about 5%. Prescriptive analytics recommends what to do about it, which is the second analyst's instruction to cut price to keep sales flat. A is wrong because using a model does not make both outputs predictive, since prescriptive analytics also uses models. The deciding factor is whether the output forecasts or recommends an action. C is wrong because this reverses the two. Forecasting the decline is predictive, and recommending the price cut is prescriptive, not the other way around. D is wrong because neither statement merely summarizes past data, so neither is descriptive. One forecasts the future and the other recommends an action. Predictive and prescriptive analytics are easy to mix up because they often show up in the same project, one right after the other. Telling them apart comes down to a single question: does the output forecast an outcome, or does it direct an action? Predictive analytics forecasts what will happen, like saying sales will fall next quarter. Prescriptive analytics recommends what to do about it, like advising a price cut to keep sales flat. The recommendation is the entire difference. The confusion happens because both types use models, both use data, and both talk about the future. None of those shared features can tell them apart, which is exactly the trap this pairing is designed to set. A simple test makes this concrete. If a statement forecasts and reports, it's predictive. If it directs an action to change the outcome, it's prescriptive. Always ask what the analysis actually tells the organization to do. If it only reports what's coming, it's predictive. If it tells them which action to take, it's prescriptive. Question 11. An analyst is asked to give the course's precise definition of big data. Which description matches it? Your options are: A. Any data set that contains more than 1 million numeric rows in a spreadsheet. B. Structured numeric data only once it grows past the capacity of a single hard drive. C. Data that has been cleaned, organized, and made ready for immediate statistical analysis. D. Both structured and unstructured data in such large volumes that it is difficult to process using traditional database and software techniques. Before I reveal it, which one do you think is right? The correct answer is D. Both structured and unstructured data in such large volumes that it is difficult to process using traditional database and software techniques. D is correct because the course defines big data as both structured and unstructured data in such large volumes that traditional database and software techniques struggle to process it. The defining features are the mix of data types and the enormous volume that defeats conventional tools. A is wrong because a fixed row count is not part of the course's definition, which centers on volumes so large that ordinary tools fall short, not on a specific threshold. Big data also includes unstructured material, not just spreadsheet rows. B is wrong because big data explicitly includes unstructured data, not structured data alone. Limiting it to structured numeric data misses half the definition. C is wrong because big data is typically messy and not analysis ready, which is why specialized data management techniques and analysts are needed. Cleaned, ready data describes the output of data management, not big data itself. Big data is a precise technical term, not just a phrase for a lot of information. Its definition packs in 3 testable ideas. The data comes in 2 forms, the volume is enormous, and that scale defeats ordinary tools. The first idea is that big data includes both structured data, like tidy rows and columns, and unstructured data, like emails, images, and video. The second idea is sheer volume, so large that conventional databases and software struggle. The third idea follows directly. Because ordinary tools fail at this scale, specialized techniques and skilled analysts are required. Structured data is the neat numeric kind that fits into rows and columns like a table of transactions. Unstructured data is everything else. The messy, non-tabular material like emails, images, and video that pours in from countless sources. It also helps to separate big data from data mining. Big data is the material, the vast and mixed body of data itself, while data mining is the activity of discovering patterns within it. Keeping the material and the activity distinct prevents a frequent error. So the reliable checklist for big data has 3 parts. It contains both structured and unstructured data. It exists in volumes too large for traditional tools, and it therefore requires specialized techniques and skilled analysts. Miss any one of these and you've missed what the term really means. Question 12. A data team lists several items they have collected. According to the course, which of the following is an example of unstructured data? Your options are A. A table of monthly sales figures arranged in rows and columns. B. Credit card transactions processed through a website. C. Videos recorded at a traffic accident site. D. A spreadsheet column listing each customer's age. What's your answer? Commit to one before I continue. The correct answer is C. Videos recorded at a traffic accident site. C is correct because the course names videos from a traffic accident site as a classic example of unstructured data because such material does not fit a traditional row and column format. It must be quantified before any analysis can be performed on it. Is wrong because a table of sales figures already sits neatly in rows and columns, which makes it structured data. It is analysis ready in its current numeric form. B is wrong because credit card transactions through a website are the course's headline example of structured data. Since each transaction has fixed fields like amount, date, and merchant, they slot directly into a table. D is wrong because a column of customers' ages is numeric data organized in a column which is structured. It requires no quantification before analysis. Let's fix the exact dividing line between structured and unstructured data because it comes up constantly in this subject. The single most reliable test is whether the data fits naturally into rows and columns of numbers. If it does, it's structured. If it doesn't, it's unstructured, and that one question resolves nearly every case. Unstructured data includes Word documents, the body of emails, videos, images, and click streams, the trails users leave as they browse. What unites them is that their meaning lives in free-form content, not fixed numeric fields. An email's a perfect trap. The free text body is unstructured, but metadata like the timestamp, sender address, and whether it was opened fits neatly into columns and is fully structured. Being unstructured doesn't mean useless. It just means the data must be quantified before statistics can touch it, by counting words, tagging images, or coding clickstream events into categories. Once quantified, this data, now more valuable than ever, becomes ready for real analysis. Question 13. A new analyst wants a clear example of structured data to explain the concept to a colleague. Which example from the course best fits? Your options are A. Credit card transactions through a website, each with a fixed set of fields. B. The free text body of a customer complaint email. C. A folder of scanned handwritten warranty cards. D. A clickstream log of raw untagged user activity. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Credit card transactions through a website, each with a fixed set of fields. A is correct because credit card transactions through a website are the course's primary example of structured data because each transaction carries a fixed set of fields such as amount, date, card number, and merchant. That fixed structure lets the data slot neatly into rows and columns for direct analysis. B is wrong because the body of an email is free text, which the course names explicitly as unstructured data. It would need to be quantified before analysis. C is wrong because handwritten warranty cards are not in a numeric row and column form and would have to be quantified first. They are unstructured rather than structured. D is wrong because a raw clickstream is listed among unstructured data types alongside text and images. It must be quantified before it can be analyzed. Let's look at structured data, the orderly counterpart to unstructured data, and the form most people picture when they think of information. The defining property is a fixed repeating structure, when every record fills the same slots with the same kinds of values, like a column of customer ages or a table of monthly sales. The data is structured, and its meaning comes from its row and column position. The headline example is a credit card transaction, amount, date, card number, and merchant all line up into a clean table, one row per transaction and one column per field, with no resistance to fitting the grid. The contrast is clear when the same purchase appears twice. The transaction record is structured and analysis ready, while the complaint email describing it is unstructured free text that still needs to be quantified. If data fits naturally into rows and columns with every record sharing the same fields, it's structured, and that readiness is why it's the starting point most analyses are built around. Question 14. A bank runs automated routines across its enormous transaction databases to surface recurring patterns it did not previously know about. According to the course, this activity is best described as which of the following? Your options are A. Big data, the large body of material being examined. B. Data mining, the process of discovering patterns in large data sets. C. Optimization, the maximizing of one variable against another. D. Recoding, the relabeling of values within a variable. Which would you go with? Lock it in before the reveal. The correct answer is B. Data mining, the process of discovering patterns in large data sets. B is correct because data mining is defined by the course as the process of discovering patterns in large data sets, and it is performed on big data. Running routines to surface recurring patterns in huge transaction databases is exactly this activity. A is wrong because big data is the material being examined, the noun, whereas the scenario describes an activity performed on it. The course keeps this distinction clear, calling data mining the process and big data the material. C is wrong because optimization is a prescriptive technique that maximizes one variable in relation to another. It is not the general activity of finding patterns in databases. D is wrong because recoding reassigns or relabels values within a variable during data management. It is not the discovery of patterns across large databases. Data mining is the process of discovering patterns in large data sets, and it's what gives big data much of its value. But the two terms are easy to blur, so let's separate them clearly. Big data is the vast mixed body of information an organization holds. Data mining is the activity performed on that material, the search for hidden patterns inside it. One is the thing, the other is what's done to the thing. Normally, large sample sizes are a blessing in statistics. But here's the irony: when a data set has enough variables and records, mining will surface a great many relationships. And most of them are coincidental rather than meaningful. 3 points anchor this topic. Data mining finds patterns in the material that is big data. Its great hazard is that coincidental correlations multiply at scale. And its blind spot is causation, since it reveals things move together while staying silent on why. Data mining is best treated as a powerful first step, generating candidates that still need careful investigation to separate real relationships from accidental noise. Question 15. A retailer's analytics platform reports thousands of statistical relationships across its massive customer database, and managers are tempted to treat each one as a cause and effect link to act on. Which course caution most directly applies to this situation? Your options are: A. Larger samples are always purely beneficial, so every relationship found is trustworthy. B. Unstructured data cannot be analyzed, so the relationships must be invalid. C. At big data scale, separating genuine causation from mere correlation becomes nearly impossible. D. Descriptive analytics cannot be performed on a database this large. Don't overthink it. Which one feels right? The correct answer is C. At big data scale, separating genuine causation from mere correlation becomes nearly impossible. C is correct because the course makes the ironic point that although large samples usually help, big data's sheer volume produces countless relationships, most of them coincidental. Distinguishing real causation from mere correlation becomes nearly impossible, which is data mining's signature challenge. A is wrong because the course warns the opposite, noting that too much data makes spurious correlations multiply. Not every relationship found at scale is trustworthy. B is wrong because unstructured data can be analyzed once it is quantified, so it is not inherently invalid. This option also misstates the actual hazard, which is confusing correlation with causation. D is wrong because descriptive analytics can certainly be run on a large database. The real caution concerns interpreting relationships, not an inability to summarize the data. Correlation and causation sound similar, but confusing them is one of the costliest mistakes a decision maker can make. Correlation just means two variables tend to move together. Causation means something stronger. One variable actually produces a change in the other. but that alignment might be coincidence or driven by a hidden third factor influencing both. So correlation alone never proves causation. Picture two variables that rise and fall together, connected only by a hidden confounding factor that actually causes them both. Neither one is causing the other, even though the data makes them look linked. At big data scale, this caution becomes a severe practical problem. Huge data sets have enormous numbers of variables, which explode into countless pairings, many showing statistical relationships by pure chance. And separating real causes from accidental correlation becomes nearly impossible. A retailer's analytics platform might surface thousands of relationships, but most are coincidences from sheer data volume. Always ask whether there's a plausible mechanism, a hidden third factor, or a test the pattern survives before calling it causal. Question 16. The McKinsey Global Institute outlined 5 broad ways big data creates value. Which of the following is not one of those 5 ways? Your options are A. Making information transparent and usable at a much higher frequency. B. Enabling narrow segmentation of customers to tailor products and services. C. Collecting more accurate, detailed performance data that exposes variability. D. Guaranteeing that any correlation found at scale reflects true causation. Got a guess? Lock it in. The correct answer is D. Guaranteeing that any correlation found at scale reflects true causation. D is correct because guaranteeing that correlation reflects causation is the opposite of what the course teaches, since at big data scale separating the two becomes nearly impossible. It is therefore not one of McKinsey's 5 value drivers. A is wrong because making information transparent and usable at higher frequency is the first McKinsey value driver. It is one of the genuine 5. B is wrong because narrow customer segmentation to tailor products and services is the third McKinsey value driver. The word segmentation anchors this item. C is wrong because collecting more accurate, detailed performance data that exposes variability and boosts performance is the second McKinsey value driver. It is a real member of the list. The McKinsey Global Institute identified 5 broad ways big data creates value for organizations, framed in business terms rather than technical ones. Knowing all 5 and telling them apart is essential since they're tested individually and as a set. First, big data makes information transparent and available at higher frequency, so decisions rest on current data. Second, it enables detailed performance measurement that reveals hidden variability. Third, it allows customer segmentation for tailored offerings. Fourth, it powers analytics that sharpen management decisions. Fifth, it fuels the creation of next-generation products and services. The second and third ways are the easiest pair to confuse. Detailed performance data exposes variability inside operations, while segmentation divides customers into narrow groups for tailored products. Anchor segmentation firmly to the word customer and the two stay distinct. Picture an organization at the center, with data flowing outward into these 5 distinct channels of value, each one a separate lever an organization can pull. One final caution: exam questions sometimes sneak in a false 6 option, like claiming big data guarantees correlation equals causation. That claim contradicts the field itself and is never one of the 5 genuine value drivers. Question 17. Google provides search, email, and mapping services free to users even though these services are costly to build and run, yet the company remains highly profitable. According to the course, how is this possible? Your options are: A. Google charges users a recurring subscription fee that covers all operating costs. B. The majority of Google's revenue comes from targeted advertising, which is most effective when there is data to mine. C. Google sells its raw structured databases directly to competing search engines. D. Government subsidies cover the cost of operating free consumer services. Which one is it? Pause the video if you need more time. The correct answer is B. The majority of Google's revenue comes from targeted advertising, which is most effective when there is data to mine. B is correct because the course explains that the majority of Google's revenue is generated through targeted advertising, which is most effective when there is data to mine. The free services generate behavioral data that lets Google predict future trends and serve relevant ads, funding the whole operation. A is wrong because the course presents these services as provided free to users, not behind a subscription. Revenue comes from advertising, not user fees. C is wrong because Google's advantage is using its data to target ads, not selling raw databases to rivals. The course frames the data as the engine of its own ad business. D is wrong because the course attributes Google's profitability to targeted advertising, not to government subsidies. No subsidy is mentioned anywhere in the example. Google is the classic example of turning big data into money. Let's trace the chain that connects free services to enormous profit. Google gives away search, email, and maps for free, even though running these services costs vast resources. So how does the company stay wildly profitable while giving so much away? Here's the mechanism made vivid. If you get an email about skiing, you're likely to see an ad for skis or lift tickets. That's not chance. It's behavioral data being mined to predict what you want, then an ad placed to match that prediction. Massive data collection feeds mining, which reveals patterns in behavior. Those patterns support predictions, and predictions guide targeted ads that generate revenue. Each link depends on the one before it, and all of it depends on having immense data to start. Without abundant data, predictions would just be guesses and ads would be untargeted. Targeted advertising, powered by data mining, is what funds services offered free to users. Question 18. In describing how big data affects daily life, the course cites Terence Mills, who notes that big data can predict the places and blocks of time that crime is likely to be committed. Which everyday application does this describe? Your options are A. Crime prevention and policing, B. Airline customer service improvements, C. Entertainment streaming recommendations, D. Video game experience design. Take a second. Which answer would you pick? The correct answer is A. Crime prevention and policing. A is correct because predicting the places and blocks of time when crime is likely to occur is the course's crime prevention and policing example, drawn from Terence Mills. The information is described as useful for police departments. B is wrong because airlines in the same list use big data to improve customer service by analyzing destinations and purchase options. That is a separate application from crime prediction. C is wrong because entertainment services use big data to customize music and movie recommendations to a user's tastes. That is recommendation, not crime forecasting. D is wrong because video gaming produces data streams used to improve gaming experiences. It is unrelated to predicting where and when crime will happen. Big data isn't just corporate strategy locked away in distant data centers. It shapes ordinary daily life in ways people rarely notice. Researcher Terence Mills catalogs many of these everyday touch points, and the common thread is behavioral data being put to work. The most familiar example is entertainment. Music and movie streaming services track what you watch and listen to, then use that feedback to sharpen recommendations. This is the recommendation engine pattern built entirely on accumulated behavioral data. A more sobering example is policing, where big data predicts the places and times crime is likely to occur. The subject matter is grave, but the method is the same one that forecasts what a shopper might buy, using historical patterns to anticipate the future. The catalog spans far more. Retailers spot credit card fraud. Healthcare tracks diseases and medication effectiveness. Social media curates each person's feed. Airlines analyze travel choices. And even video games mine data to improve play. Remember that Mill's catalog of everyday uses is a distinct list from the McKinsey value drivers. Wax Salensal. One shows how big data touches daily life, the other how it creates economic value. And matching crime prediction specifically to policing keeps the two straight. Question 19. A research team has gathered a large collection of customer service call transcripts, product photos, and website click streams. Before they can run statistical analysis on this material, what does the course say must happen? Your options are: A. The material must be deleted since unstructured data cannot contribute to analysis. B. The material must be stored in a relational database without any further processing. C. The material must be quantified since unstructured data must be turned into numbers before analysis. D. The material must be converted from ratio data into interval data. Before I reveal it, which one do you think is right? The correct answer is C. The material must be quantified since unstructured data must be turned into numbers before analysis. C is correct because the course states that unstructured material such as text, images, and click streams must be quantified before analysis can be performed. Turning transcripts, photos, and click streams into numbers is exactly that required transformation step. A is wrong because unstructured data is not unusable, so deletion is wrong. The course says it simply must be quantified first. B is wrong because storing data in a database organizes it but does not by itself turn text and images into the numbers analysis requires. Quantification is still needed. D is wrong because interval and ratio are levels of measurement for numeric scales, not a conversion that turns transcripts and photos into analyzable data. The needed step is quantification, not a change of measurement level. Before any statistical analysis can happen, unstructured data must be turned into numbers. This isn't a footnote, it's a required processing step called quantification. Unstructured data includes text, images, and click streams, the bodies of emails, documents, photographs, and trails of clicks. This material carries real meaning, but that meaning is locked in a form statistics cannot directly read. Quantification means converting free-form content into numeric standards. Text gets counted or scored for sentiment. Images get tagged and counted. And click streams get coded into categories and tallied. This is a form of transforming data, one of the core data management techniques. A pile of transcripts becomes a table of word counts and sentiment scores. The original isn't discarded, but a numeric companion is created that statistics can finally use. Unstructured data carries an extra cost of preparation, but once quantified, it often reveals richer insight than the structured data you already had. The required step is always quantification, not deletion, not storage. Question 20. A statistician notes that while large samples usually strengthen analysis, big data presents a surprising downside. Which statement best captures the course's counterintuitive point about big data's volume? Your options are: A. Big data is always too small to reveal meaningful patterns. B. More data uniformly improves the ability to prove causation. C. Large volumes make every analysis cheaper and simpler to interpret. D. Ironically, one problem with big data is that there is too much of it, which makes separating causation from correlation nearly impossible. What's your answer? Commit to one before I continue. The correct answer is D. Ironically, one problem with big data is that there is too much of it, which makes separating causation from correlation nearly impossible. D is correct because the course makes the deliberately ironic observation that although large sample sizes are usually beneficial, one problem with big data is that there is too much of it. That overload makes parsing relevant data and telling causation from correlation nearly impossible. A is wrong because big data is defined by enormous volume, not by being too small. The scenario concerns having too much data, not too little. B is wrong because the course argues that at scale, proving causation becomes harder, not easier, because coincidental correlations multiply. More data does not uniformly improve causal proof. C is wrong because large volumes introduce interpretation difficulties rather than removing them. The course frames big data's scale as a source of analytical hazard, not simplicity. There's a counterintuitive lesson at the heart of big data. In ordinary statistics, more data is almost always better, but at massive scale, that instinct runs into trouble. Ironically, one of the biggest problems with big data is that there's simply too much of it. Past a certain point, abundance doesn't clarify the picture. It obscures it, making genuine causation nearly impossible to separate from mere correlation. The mechanism is simple. With enough variables and enough rows, countless pairs of things will appear to move together purely by chance. A mining process turned loose on such a data set returns a flood of relationships, and most of them are accidental rather than meaningful. The practical response isn't to fear large data, but to approach it with discipline. Be deliberate about which variables matter, skeptical of relationships with no plausible mechanism, and willing to test patterns rather than trust them. Remember, bigger samples help in the classical statistical sense, but at big data scale, that same growth makes separating causation from correlation far harder. Both truths hold at once. Question 21. A new analyst wants to follow the Davenport-Kim 3-stage model so that the work stays, in the course's phrase, guided rather than rambling. In what order do the 3 stages occur? Your options are A. Framing the problem, then solving the problem, then communicating results. B. Solving the problem, then framing the problem, then communicating results. C. Communicating results, then framing the problem, then solving the problem. D. Framing the problem, then communicating results, then solving the problem. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Framing the problem, then solving the problem, then communicating results. A is correct because the Davenport-Kim model runs in the order of framing the problem, solving the problem, and communicating results. Framing first is what keeps the analysis guided rather than rambling, since a clear question disciplines everything that follows. B is wrong because solving cannot come before framing, because without a framed question, the analysis has no direction. The course is explicit that framing comes first. C is wrong because communicating results is the final stage, not the first. Putting it first would mean presenting conclusions before any analysis exists. D is wrong because solving must precede communicating, since there are no results to communicate until the problem has been solved. This option swaps the last 2 stages. Good data analytics never starts with data or math. It starts with a real question an organization needs answered, so the research stays guided instead of rambling. Without a framing question, effort scatters across whatever happens to be measurable instead of what actually matters. A model imposes discipline by forcing every step to serve a defined purpose from the start. The model has 3 stages, and the order is essential. First, framing the problem. Second, solving the problem. Third, communicating results. Framing must come first because until the problem is defined, there is nothing to solve. And communicating comes last because it carries finished findings to the people who act on them. Each stage holds its own internal steps. Framing breaks into problem recognition and reviewing previous findings. Solving involves modeling, data collection, and data analysis, and communicating means crafting the story and delivering it to stakeholders. Choices made while framing, like identifying stakeholders and the story to tell, shape how much solving is needed and who hears the results. Keep the stages and their sub-steps straight, and the sequence stops being a checklist and starts being a loop that drives real decisions. Question 22. During the framing stage, the course warns analysts not to get too specific about the experiment too early, lest they miss an important avenue of investigation, and only afterward to focus on a narrow set of data. Which pair of problem recognition steps does this wide then narrow movement describe? Your options are A. Identifying stakeholders, then focusing on decisions. B. Reviewing previous findings, then identifying the story to tell. C. Determining the scope of the problem, then getting specific about what to find out. D. Focusing on decisions, then identifying stakeholders. Which would you go with? Lock it in before the reveal. The correct answer is C. Determining the scope of the problem, then getting specific about what to find out. C is correct because determining the scope of the problem is the step where the course warns against over-specifying so as not to miss an important avenue of investigation. Getting specific about what to find out is the later step where the analyst narrows to the data to analyze, producing the wide then narrow movement. A is wrong because identifying stakeholders and focusing on decisions are the first two problem recognition steps, concerned with who cares and what decision is at stake. They do not describe the broad then narrow scoping motion. B is wrong because reviewing previous findings is a separate part of framing, and identifying the story is a different step. Neither captures the explicit scope then specifies sequence. D is wrong because this reverses two early steps and omits the scope and specificity steps entirely. The wide then narrow caution is about scope followed by specificity, not stakeholders and decisions. Framing the problem, the first stage of the Davenport-Kim model, has two parts: problem recognition and a review of previous findings. Together they make sure work starts with a clear target and an awareness of what's already known. Problem recognition unfolds in 5 steps: identifying stakeholders, focusing on decisions, identifying the kind of story to tell, determining scope, and getting specific. Identifying stakeholders matters most up front, since without committed stakeholders, even a correct analysis goes nowhere. The 4th and 5th steps embody a key principle. When determining scope, avoid getting too specific too early. Only after surveying the big picture should the analyst narrow to the specific data that will be analyzed. Getting specific too early is a genuine named error. If an analyst narrows down before understanding the broader situation, promising lines of inquiry may never even be considered, and the cost is silent because it's never noticed. The second part of framing, reviewing previous findings, plays 2 roles. It helps structure the analysis using approaches that worked before, and it supplies ideas for telling the story once analysis is complete. Skipping this review risks reinventing work or missing context that would sharpen the new analysis. Question 23. Within problem recognition, the course singles out the step of focusing on decisions as especially important and gives 3 reasons for asking what decisions will be made as a result of the analysis. Which option correctly lists those 3 reasons? Your options are: A. It selects the statistical software, identifies the sample size, and sets the budget. B. It identifies the reason for the analysis, identifies key stakeholders, and determines whether the analysis is worth doing. C. It guarantees valid data, eliminates bias, and ensures reliability. D. It frames the story, collects the data, and communicates the results. Don't overthink it. Which one feels right? The correct answer is B. It identifies the reason for the analysis, identifies key stakeholders, and determines whether the analysis is worth doing. B is correct because the course states that asking what decisions will be made helps identify the reason for the analysis, identify key stakeholders, and determine whether the analysis is worth doing. If no decision hinges on the answer, the analysis may not be worth the effort. A is wrong because selecting software, sizing the sample, and setting a budget are practical tasks. But they are not the three reasons the course attaches to focusing on decisions. The course's three reasons concern purpose, stakeholders, and worth. C is wrong because guaranteeing validity, eliminating bias, and ensuring reliability are data quality and research design concerns from other chapters. They are not the three reasons tied to focusing on decisions. D is wrong because framing, collecting, and communicating are stages or steps of the broader model, not the three reasons for focusing on decisions. This option confuses the model structure with the specific steps rationale. Among the 5 steps of problem recognition, 1 is singled out for special emphasis, focusing on decisions. That means asking, right at the outset of any analysis, what decisions will actually be made as a result of the work? The material attaches 3 specific reasons to this step. First, it identifies the reason for the analysis, since naming the decision clarifies why the work exists. Second, it identifies the key stakeholders, because whoever makes or is affected by that decision is a stakeholder. Third, and most pointed, it determines whether the analysis is worth doing at all. This third reason is a bracing test. Analysts often launch studies out of habit or curiosity that end up changing nothing. So tying the work to a genuine decision filters out effort destined to be ignored. It helps to separate this from things it resembles. The 3 reasons aren't about choosing software, sizing a sample, or setting a budget, and they aren't about guaranteeing validity or eliminating bias. Those belong to later, practical stages, not to the initial framing question. So the cleanest way to hold this, focusing on decisions identifies purpose, reveals stakeholders, and gauges worth, all in one question. That decision-first habit is one of the most practical lessons the entire model teaches. Question 24. A company wants to study sales by different age demographics and build a simplified representation that includes only the variables sales and age, leaving out the thousands of other factors that exist in reality. According to the course, what has the company created and in which stage does this step belong? Your options are A construct created during the communicating results stage, B, a sample created during the framing stage, C, a record created during the data collection step, D, a model created during the solving stage. Got a guess? Lock it in. The correct answer is D, a model created during the solving stage. D is correct because the course defines a model as a simplified representation meant to solve a particular problem, and the modeling step opens the solving stage where the mathematical heavy lifting takes place. Isolating just sales and age while ignoring other factors is exactly the deliberate simplification a model performs. A is wrong because a construct is an abstract concept made into a quantifiable variable, not a simplified representation of a problem. The communicating results stage is also the wrong stage for building the model. B is wrong because a sample is a representative subset of a population, not a representation that isolates chosen variables. Building the model belongs to solving, not framing. C is wrong because a record is all the data for one subject, typically a row, not a simplified representation of a problem. It is not created as a distinct modeling step. The solving stage is the second part of the Davenport-Kim model, where the actual analytical work happens. It unfolds in 3 ordered steps: modeling, data collection, and data analysis. The modeling step begins with a precise idea. A model is a simplified representation meant to solve a particular problem. Reality has countless variables, so a useful model deliberately ignores almost all of them, keeping only the ones that matter. Consider a company studying its advertising by age demographic. The model isolates just two variables, sales and age, deliberately setting aside every other factor about the business and its customers. After modeling comes data collection, gathering data from primary or secondary sources and quantifying anything unstructured. Then comes data analysis, finding patterns whose depth depends on the story chosen back in the framing stage. All three steps, modeling, collection, and analysis, belong to the solving stage, and a model's deliberate simplicity is exactly what makes it useful. Question 25. An analyst assumes that the real work of a project is the mathematics and treats the final presentation of findings as an afterthought. According to the course's view of the Davenport-Kim model, why is this assumption a mistake? Your options are: A. Communicating results is where the model is first built and the variables are chosen. B. Communicating results is optional and can be skipped once the analysis is sound. C. Although it may seem least important, communicating results is essential if findings are to result in action. D. Communicating results is a stage where stakeholders are first identified. Which one is it? Pause the video if you need more time. The correct answer is C. Although it may seem least important, communicating results is essential if findings are to result in action. C is correct because the course explicitly warns against undervaluing communication, stating that although you may think it is the least important part, it is essential if you want your findings to result in action. Analysis that is never understood or acted upon is wasted. A is wrong because the model is built during the solving stage, not while communicating results. This option misplaces the modeling step. B is wrong because the course's whole point is that communication is not optional, but essential for driving action. Skipping it defeats the purpose of the analysis. D is wrong because stakeholders are first identified during framing, in problem recognition, not during communication. Communication is where results are delivered to those already identified stakeholders. Communicating and acting on results is the third and final stage of the Davenport-Kim model, and it's tempting to treat it as a mere formality after the real math is done. The material warns directly against that assumption. A flawless analysis produces nothing of value if its conclusions sit unread or fail to persuade the people who could act on them. The entire point of the workup, set up back in framing, is to drive a decision, and a decision requires results communicated clearly to stakeholders positioned to act. Communication carries finished findings across the gap between knowing something and doing something about it. Good results don't speak for themselves. They must be shaped into a clear story, delivered in a form the audience can grasp, and tied explicitly to the decision at hand. Consider an analyst who uncovers a genuine finding. Buried in dense tables and delivered defensively, it may never be absorbed and the problem persists, presented through clear charts and a coherent narrative tied to the choice at hand. Stakeholders understand and can act. This stage closes the loop begun in framing when stakeholders and their story were first chosen. Communication may seem like the least important step, but it's essential for findings to ever become action. Question 26. An analyst notes that a person's age can take a value like 22.67 years, lying anywhere along a range, whereas the number of cars a household owns can only be a whole number such as 3 or 4. Which distinction does this contrast illustrate? Your options are: A. Age is continuous data, while the number of cars is discrete data. B. Age is discrete data, while the number of cars is continuous data. C. Both age and number of cars are continuous data. D. Both age and number of cars are discrete data. Take a second, and which answer would you pick? The correct answer is A. Age is continuous data, while the number of cars is discrete data. A is correct because continuous data can lie along any point in a range, and the course uses age, which can be 22.67 years, as its example. Discrete data takes only whole values with clear boundaries, and the course uses number of cars, since you cannot own a fractional car, as its example. B is wrong because this reverses the two. Age is the continuous example, and number of cars is the discrete example, not the other way round. C is wrong because number of cars cannot be continuous because it only takes whole values with clear boundaries. Only age fits the continuous definition here. D is wrong because age is not discrete because it can take fractional values like 22.67 years. It is the course's example of continuous data. Before the 4 levels of measurement, there's a more basic split you need to understand: continuous versus discrete data. This distinction is foundational because the 4 levels map directly onto it. Continuous data can take any value along a range, with another value always possible in between. Age is the classic example, since a person can be 22 and a half, flowing smoothly without any fixed step size. Discrete data, on the other hand, can only take whole separated values. The number of cars a household owns is the standard example. You can own 3 or 4, but never a fraction in between. This split matters because nominal and ordinal data are types of discrete data, while interval and ratio data are types of continuous data. The 2 label-like levels sit on the discrete side, and the 2 numeric levels sit on the continuous side. Remember, the distinction is about whether intermediate values are truly possible, not how a number is written down. Age rounded to whole years is still continuous, and a car count is still discrete no matter how it's displayed. Question 27. A survey records each respondent's gender purely as a label, with no ranking or quantity attached to the categories. Which level of measurement does this represent? Your options are A. Ratio, because the categories can be compared as multiples. B. Interval, because the categories are an equal distance apart. C. Ordinal, because the categories can be ranked from low to high. D. Nominal, because the data labels subjects without ranking or quantifying them. Before I reveal it, which one do you think is right? The correct answer is D. Nominal, because the data labels subjects without ranking or quantifying them. D is correct because nominal data, sometimes called categorical data, labels subjects by placing them into a category rather than attaching a quantity, and the course uses gender as its example. The categories have no inherent rank or numeric value, which is exactly the case described. A is wrong because ratio data has a true zero and supports multiplication, neither of which applies to gender categories. Labels cannot be compared as multiples. B is wrong because interval data has equal, meaningful intervals between values, but gender categories are not spaced along a numeric scale. There is no meaningful distance between the labels. C is wrong because ordinal data ranks objects by some quality, but gender categories carry no inherent order. One category is not higher or lower than another. Nominal data is the simplest of the 4 levels of measurement. It sorts subjects into categories, but those categories carry no order and no quantity, just names. Classic examples include eye color, blood type, marital status, and type of pet. Each simply assigns a subject to a group with no category being higher, larger, or better than another. Take gender as the anchor example. Subjects are sorted into categories, but no category outranks another. It's classification, not measurement. Nominal data only supports 2 operations, sorting subjects into groups and counting how many fall into each. It never supports ordering or averaging, since the categories are discrete labels with no values between them. Don't be fooled by a small number of categories. That alone never makes data ordinal. The real test is whether categories carry an inherent rank. If not, it's nominal, no matter how many groups exist. Question 28. A martial arts program records each student's rank, noting that a third-degree black belt is presumed to have more expertise than a first-degree black belt, though the exact gap in skill between ranks is not measured. Which level of measurement does this represent? Well, options are A. Nominal, because the belts are simply labels with no order. B. Ordinal, because the belts are ranked by a quality, but the intervals between them are not equal or measured. C. Interval, because the gap between each belt degree is equal and meaningful. D. Ratio, because a third-degree belt has exactly 3 times the expertise of a first-degree belt. What's your answer? Commit to one before I continue. The correct answer is B. Ordinal, because the belts are ranked by a quality, but the intervals between them are not equal or measured. B is correct because ordinal data places objects in an order according to some quality, where a higher position means more of that quality, and the course uses black belt degree as its example. The ranks are ordered, but the intervals between them are not equal or meaningfully measured, which matches the unmeasured skill gap described. A is wrong because the belts are not mere labels, because they carry a clear order of increase in expertise. That ordering is what makes the data ordinal rather than nominal. C is wrong because interval data requires equal, meaningful intervals between values, but the gap in expertise between belt degrees is not measured or equal. Ordinal ranks deliberately lack that equal spacing. D is wrong because ratio data would allow saying one value is exactly 3 times another, but expertise across belt degrees cannot be multiplied that way. The course treats belt degree as ordinal, not ratio. Ordinal data is the second level of measurement. It adds exactly one new power that nominal data lacks, the power of order, letting us rank categories from less to more. Think of survey ratings like poor, fair, good, and excellent, or military ranks, class standing, and race finishes. In each case, categories line up along some underlying quality from low to high. Take the classic example, black belt degrees in karate. A third-degree belt has more expertise than a first-degree belt, but we can't say it's exactly twice as much, or 2 measured units more, because the spacing between ranks was never actually measured. The ranking itself is meaningful, but the distances between the rungs of that ladder are not. That's the single most important fact about ordinal data, and it's why you can compare ranks as greater or lesser, but never subtract or multiply them. Ordinal data stays discrete, separate ranked categories with no measurable point in between. Order without measured spacing is the signature of ordinal data. Question 29. A researcher records the time of day for a series of events, noting that each minute is an equal, meaningful interval apart, but that the starting point of midnight is arbitrary and does not represent the absence of time. Which level of measurement is being used? Your options are A. Interval data, which has equal intervals and an order but no true zero. B. Ratio data, because midnight represents a true absence of time. C. Ordinal data, because times can only be ranked, not measured. D. Nominal data, because each time is just a category. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is A. Interval data, which has equal intervals and an order but no true zero. A is correct because interval data has order and equal, meaningful intervals but no natural zero, and zero does not represent the absence of the property. The course names time of day as a canonical interval example, with midnight as an arbitrary starting point rather than an absence of time. B is wrong because ratio data requires a true zero that represents none of the property, but midnight does not mean the absence of time. The arbitrary zero is precisely why time of day is interval, not ratio. C is wrong because ordinal data only ranks objects without equal intervals. Yet each minute here is an equal, meaningful distance apart. That equal spacing places the data above the ordinal level. D is wrong because nominal data is unordered labels, but time of day clearly has both order and measured intervals. It is far more informative than a nominal label. Interval data is the third level of measurement, and it adds something ordinal data lacked, equal, meaningful spacing between values. It has an order like ordinal data. Its values are an equal interval apart, so differences are meaningful, and critically, it has no true zero point that represents the absence of the property being measured. The two classic examples are time of day and Fahrenheit temperature. Each minute or degree is an equal, meaningful interval apart, yet midnight and 0 degrees are just arbitrary starting points, not the absence of time or heat. Because 0 is arbitrary, addition and subtraction still work perfectly, but multiplication and ratios break down. 80 degrees is not twice as hot as 40 degrees, because doubling the number doesn't double any real amount of heat. So the test is simple. Check whether 0 means none of the thing. If 0 is just a starting point and the property still exists there, you're looking at interval data, good for differences, not for multiples. Question 30. A financial analyst models the income of various executives, noting that $0 represents no money at all and that $100 is twice as much as $50. Which level of measurement is being used and why? Your options are A. Interval, because income has an arbitrary 0 point. B. Ordinal, because incomes can only be placed in rank order. C. Ratio, because income has a true 0 and values can be compared as multiples. D. Nominal, because each income figure labels a different executive. Which would you go with? Lock it in before the reveal. The correct answer is C. Ratio, because income has a true 0 and values can be compared as multiples. C is correct because ratio data has a unique true 0 and allows values to be compared as multiples, and the course names income and money as examples. $0 means no money at all, and $100 being twice $50 is exactly the multiple comparison ratio data permits. A is wrong because interval data lacks a true 0, but income has a genuine 0 at $0 that represents the absence of money. That true 0 rules out interval and points to ratio. B is wrong because income can be ranked, but it also supports equal intervals and meaningful multiples, which goes far beyond the ordinal level. Calling it ordinal ignores its true 0 and ratio comparisons. D is wrong because income figures are quantities, not mere labels for executives. Nominal data attaches no quantity, whereas income is fully numeric with a true 0. Ratio data is the fourth and most informative level of measurement, and it adds the one property interval data lacked, a true 0. That true 0 is what makes multiplying and dividing values meaningful, not just adding and subtracting them. A true 0 is a value where the quantity genuinely does not exist. None of it is present, unlike a merely convenient starting point, because that 0 marks real absence. Doubling or halving the number corresponds to doubling or halving an actual amount, which is why ratio data supports full arithmetic, including multiplication. Age is the central example. A person can be twice as old as another, and 0 years old is a genuine starting point of no accumulated age. Money works the same way, since a natural 0 sits at no dollars, and $100 is genuinely twice as much as 50. Income, stock price, amount of inventory, and number of repeat customers are all ratio data, because each has a unique 0 point and can be compared through multiplication. 0 inventory means none in stock. 0 repeat customers means none returning. And $0 means no money at all. To recognize ratio data, ask 2 questions that always agree. Does 0 mean complete absence? And is twice as much a meaningful comparison? A yes to both marks the data as ratio. Question 31. An analyst applies the natural 0 test to 4 variables, asking whether 0 means a complete absence of the thing being measured. For which variable does 0 represent a true absence, marking it as ratio data? Your options are a temperature measured in degrees Fahrenheit, B, the time of day on a 24-hour clock, C, the calendar date of an event, D, the number of repeat customers a business has. Don't overthink it. Which one feels right? The correct answer is D, the number of repeat customers a business has. D is correct because the natural 0 test asks whether 0 means none of the thing being measured, and 0 repeat customers genuinely means the business has none. The course lists number of repeat customers among its ratio examples for exactly this reason. A is wrong because 0 degrees Fahrenheit is a specific cold temperature, not the absence of temperature, so it fails the natural 0 test. Fahrenheit is therefore interval, not ratio. B is wrong because midnight on a clock is an arbitrary starting point, not the absence of time, so time of day fails the natural 0 test. It is a classic interval example. C is wrong because a calendar date uses an arbitrary 0 point and does not represent the absence of time. Like time of day, dates are interval rather than ratio. There's one question that instantly tells interval data apart from ratio data. Does 0 mean a complete absence of the thing being measured? When 0 represents none of the quantity, the scale measures real amounts up from true emptiness, and that's exactly what makes multiplying and comparing ratios valid. But when 0 is just a chosen starting point, the numbers don't measure from nothing, so multiples become meaningless. $0 means no money at all, and 0 years old means no age has accumulated, so both pass as ratio. But 0 degrees Fahrenheit still holds real thermal energy, and midnight is just where clock counting begins. So both are interval. Notice the discipline trick. Ask what 0 would mean, not whether 0 appears in the data. Temperatures can dip below the Fahrenheit 0, proving it isn't a true flaw, while money simply cannot go below a genuine 0. So remember, a yes points to ratio, like money, age, and customer counts, and a no points to interval, like temperature and time. This test pairs perfectly with the compare as multiples check to confirm your answer. Question 32. A student is asked why the Fahrenheit temperature scale is classified as interval data rather than ratio data. Which explanation is correct? Your options are A, because warmer temperatures cannot be ranked above cooler ones. B, because the degree intervals are equal and meaningful, but 0 degrees Fahrenheit does not represent the absence of temperature. C, because Fahrenheit temperatures are mere labels with no order. D, because 80 degrees Fahrenheit is exactly twice as hot as 40 degrees Fahrenheit. Got a guess? Lock it in. The correct answer is B, because the degree intervals are equal and meaningful, but 0 degrees Fahrenheit does not represent the absence of temperature. B is correct because Fahrenheit is interval, because its degree intervals are equal and meaningful, yet 0 degrees Fahrenheit is a real temperature rather than the absence of temperature. With no true 0, ratio comparisons are not valid, which keeps the scale at the interval level. A is wrong because Fahrenheit temperatures can certainly be ranked, since warmer is higher than cooler. The reason it is interval rather than ratio is the lack of a true zero, not a lack of order. C is wrong because Fahrenheit values are ordered measurements, not unordered labels. They carry both order and equal intervals, which is more than nominal labeling. D is wrong because saying 80 degrees Fahrenheit is twice as hot as 40 is meaningless, precisely because the scale lacks a true zero. That impossibility is what makes it interval, so this statement is the opposite of correct. Fahrenheit temperature is one of the two classic examples of interval data, and knowing exactly why reveals one of the most tested ideas in measurement theory. Fahrenheit has order, since warmer readings clearly rank above cooler ones, and it has equal intervals, since the gap between any two adjacent degrees is uniform. Because of this, subtraction works perfectly. The difference between 40 and 50 degrees equals the difference between 70 and 80. What Fahrenheit lacks is a true zero. 0 degrees Fahrenheit is just a specific cold reading, not an absence of thermal energy. And the proof is that the same physical condition carries a different, non-zero number on other temperature scales. Because 0 doesn't mean none. Multiplying a Fahrenheit value multiplies nothing physical. So it's meaningless to say 80 degrees is twice as hot as 40. Differences work, multiples do not. And that single missing true zero is the entire reason Fahrenheit stops at interval level. So whenever Fahrenheit appears, recall the chain. Equal intervals make differences meaningful, but the arbitrary zero makes ratio comparisons invalid. Fixing it firmly as interval data. Question 33. Comparing temperature scales, a student notes that the Kelvin scale has a unique zero value called absolute zero. Why does this make Kelvin ratio data while Fahrenheit is only interval? Your options are absolute zero genuinely represents the total absence of thermal energy, giving Kelvin a true zero that supports ratio comparisons. B. Kelvin has no order, so it must be ratio by default. C. Kelvin degrees are unequal in size, which qualifies the scale as ratio. D. Kelvin is ratio only because its numbers are larger than Fahrenheit numbers. Which one is it? Pause the video if you need more time. The correct answer is A. Absolute zero genuinely represents the total absence of thermal energy, giving Kelvin a true zero that supports ratio comparisons. A is correct because the Kelvin scale zero is absolute zero, which represents the complete absence of thermal energy with no temperature possible below it. That genuine true zero is what allows ratio comparisons and makes Kelvin ratio data, unlike Fahrenheit's arbitrary zero. B is wrong because Kelvin clearly has order with higher numbers meaning more thermal energy. The feature that makes it ratio is its true zero, not an absence of order. C is wrong because Kelvin degrees are equal in size, just like the intervals on other temperature scales. Equal intervals plus a true zero are what make it ratio, so unequal degrees is false. D is wrong because the size of the numbers is irrelevant to the level of measurement. What matters is that Kelvin has a true zero at absolute zero, not that its figures look larger. Kelvin and Fahrenheit both measure temperature, yet Kelvin is ratio data, while Fahrenheit is only interval. The entire difference comes down to one thing: the nature of the 0 point. Absolute zero on the Kelvin scale represents the total absence of thermal energy. Nothing can be colder, because there is no energy left to remove, making it a genuine, real zero rather than an arbitrary starting point. On Kelvin, 0 degrees truly means zero thermal energy. On Fahrenheit, 0 degrees is just an arbitrary marker that corresponds to a non-zero value on other scales, exposing it as an arbitrary origin. This reveals something deeper. The level of measurement is a property of the scale you choose, not of the underlying phenomenon. Temperature never changes, but measuring it with an arbitrary zero gives interval data, while measuring it with a true zero gives ratio data. Kelvin's absolute zero means real thermal energy can be doubled or halved meaningfully, unlike Fahrenheit. This Kelvin-Fahrenheit pair is one of the most frequently tested ideas in levels of measurement. Question 34. An analyst uses the compare as multiples test, asking whether it makes sense to say one value is some number of times another. For which statement is such a multiple comparison valid, indicating ratio data? Your options are A. 3 o'clock is 3 times as late as 1 o'clock. B. 60 degrees Fahrenheit is twice as warm as 30 degrees Fahrenheit. C. A person who is 40 years old is twice as old as a person who is 20. D. The year 2000 is twice as much time as the year 1000. Take a second. Which answer would you pick? The correct answer is C. A person who is 40 years old is twice as old as a person who is 20. C is correct because the compare as multiples test is valid only for ratio data with a true zero, and age qualifies because 0 years means no age accumulated. Saying a 40-year-old is twice as old as a 20-year-old is therefore a legitimate ratio comparison. A is wrong because clock time is interval data with an arbitrary zero, so calling 3 o'clock 3 times as late as 1 o'clock is meaningless. The multiple comparison fails without a true zero. B is wrong because Fahrenheit temperature is interval, so 60 degrees is not twice as warm as 30 degrees. The absence of a true zero makes this multiple comparison invalid. D is wrong because calendar years use an arbitrary zero, so the year 2000 is not twice as much time as the year 1000. Dates are interval and do not support multiple comparisons. There's a second way to tell interval data from ratio data, and it works from the opposite direction of the natural zero test. Instead of asking what zero means, it asks whether one value can sensibly be called some number of times another. A statement like twice as much is secretly measured from zero, and it only makes sense if that zero represents genuine absence. When zero truly means none, doubling doubles a real amount. When zero is arbitrary, doubling doubles nothing real. For age, money, and inventory, the multiple is real. 40 years old is genuinely twice 20, because age has a true zero at birth. But 3 o'clock is not 3 times as late as 1 o'clock, and 60 degrees Fahrenheit is not twice as warm as 30, because clock time and Fahrenheit have no genuine zero to measure from. Picture 2 number lines side by side. One starts at a true zero, like birth for age, so the jump from 20 to 40 really is a doubling. The other starts at an arbitrary zero, like Fahrenheit, so the jump from 30 to 60 looks like doubling but describes nothing real. Whichever test you find easier, the natural zero test or this one, they always agree because both are really asking whether the scale has a meaningful origin. Question 35. A student observes that temperature can be either interval data or ratio data depending on whether it is measured in Fahrenheit or Kelvin. What general principle about levels of measurement does this illustrate? Your options are A. The level of measurement is fixed by the physical phenomenon and never changes. B. The level of measurement is a property of the measurement scale, not of the underlying phenomenon. C. All temperature measurements are nominal because they use named units. D. Continuous phenomena can never be measured at the ratio level. Before I reveal it, which one do you think is right? The correct answer is B. The level of measurement is a property of the measurement scale, not of the underlying phenomenon. B is correct because the Fahrenheit versus Kelvin contrast shows that the same physical quantity can be interval on one scale and ratio on another. The course's teaching point is that the level of measurement belongs to the scale used, not to the phenomenon itself. A is wrong because if the level were fixed by the phenomenon, temperature could not be interval in Fahrenheit and ratio in Kelvin. The example proves the level is not fixed by the phenomenon. C is wrong because temperature scales are ordered numeric measurements with equal intervals, not unordered labels, so they are not nominal. Naming the unit does not make the data categorical. D is wrong because ratio is a continuous level, and Kelvin is a continuous ratio scale, so continuous phenomena certainly can be measured at the ratio level. The statement contradicts the Kelvin example. Here's a key idea that's easy to forget. The level of measurement belongs to the scale you use, not to the thing you're measuring. Take temperature. Measured in Fahrenheit, it's interval data because its zero is arbitrary. Measured in Kelvin, it's ratio data because zero there means a true absence of temperature. The phenomenon never changed, only the scale did. If the level were a fixed property of temperature itself, it couldn't change depending on which scale you used. Since it clearly does change, the level must belong to the scale, not the phenomenon. This is why an analyst can never classify a reading just by looking at the phenomenon. You have to check how it's operationalized, what units are used, and especially where zero falls. These are all choices about measurement, not facts about the world. So when a question asks what general truth the Fahrenheit-Kelvin contrast illustrates, the answer is this: it's the scale, not the underlying thing, that fixes the level of measurement. Question 36. A testing service administers the same assessment to the same person 3 times, and the scores come out very similar each time. According to the course, what property does this consistency demonstrate? Your options are A. Validity, because the test measures what it intends to measure. B. Content validity, because the test is neither too wide nor too narrow. C. Internal validity, because no bias entered the data. D. Reliability, because the results are consistent and repeatable. What's your answer? Commit to one before I continue. The correct answer is D. Reliability, because the results are consistent and repeatable. D is correct because reliable data is consistent and repeatable, and the course's own test is whether the same assessment given to the same person multiple times yields similar scores. Similar scores across 3 administrations is exactly that demonstration of reliability. A is wrong because validity concerns whether the test accurately measures the intended trait, which consistency alone does not establish. A test can be consistent yet still measure the wrong thing. B is wrong because content validity asks whether the construct measures what it claims without being too wide or too narrow. Repeatable scores speak to stability, not coverage. C is wrong because internal validity concerns whether bias entered the collected data. Getting similar scores on repeat administrations addresses consistency, not freedom from bias. Reliability is one of 2 core qualities a measurement must have, and it has a precise meaning. Reliable data is consistent and repeatable. If the same test on the same person gives similar results each time, it's reliable. Picture stepping on a bathroom scale 3 times in a minute. If it shows nearly the same weight each time, it's reliable because its readings are consistent. If it jumps from one number to a very different one, it's unreliable, since no single reading can be trusted. The stable scale gives nearly identical readings every time it's used, showing steady, reproducible results. The erratic scale gives wildly different readings on the same unchanging weight, which is exactly what makes it unreliable. Here's the crucial trap. Reliability says nothing about whether a measurement is correct, only whether it's stable. A scale that always reads 10 pounds too high is perfectly reliable, because it repeats the same wrong number every time. That's why consistency is necessary but never sufficient for trustworthy data. So when you see steady, reproducible results, that's reliability. Wild swings mean unreliability, and a consistently wrong answer is still technically reliable. Question 37. A test is designed to measure students' math ability and it genuinely reflects their math aptitude rather than their reading speed or test-taking tricks. According to the course, which property does the test possess? Your options are A. Reliability, because the scores are repeatable. B. Discreteness, because scores are whole numbers. C. Validity, because it accurately measures what it is intended to measure. D. Optimization, because it maximizes student scores. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Validity, because it accurately measures what it is intended to measure. C is correct because valid data results from a test that accurately measures what it is intended to measure, which the course illustrates with a test that accurately reflects students' aptitudes. A math test that truly captures math ability rather than something else is the definition of validity. A is wrong because reliability concerns consistency across repeated measurements, not whether the test measures the right trait. Accurately reflecting math ability is about accuracy, which is validity. B is wrong because whether scores are whole numbers concerns levels of measurement, not the test accuracy. Discreteness is unrelated to measuring the intended trait. D is wrong because optimization is a prescriptive analytics technique for maximizing one variable against another. It has nothing to do with whether a test measures what it intends. Validity is the second key quality of sound measurement, alongside reliability, but it asks a different question. While reliability asks if a measurement is consistent, validity asks if it is accurate, whether the instrument truly captures the trait it claims to measure. A measurement is valid when it hits the intended target, not merely when it lands in the same place every time. A valid math test genuinely measures math ability, rather than reading speed, test-taking tricks, or how rested a student feels. Consider a bathroom scale that always reads 10 pounds too high. It is reliable because it is consistent, but it is not valid because it fails to report true weight. This proves accuracy and consistency are independent qualities, because valid data isn't found by coincidence. Studies with valid measurements tend to replicate when different researchers repeat them. A genuine finding holds up under independent hands, while a result that disappears on retesting should raise suspicion. Good decisions require measurements that are both valid and reliable, accurate and stable together. Validity supplies the accuracy half of that equation, something no amount of mere consistency can ever provide. Question 38. A bathroom scale reads exactly 8 pounds too heavy every single time it is used. How should the scale be described? And what lesson does it illustrate? Your options are A. Reliable but not valid, showing that consistency does not guarantee accuracy. B. Valid but not reliable, showing that accuracy does not guarantee consistency. C. Both reliable and valid, since it always gives the same reading. D. Neither reliable nor valid, since any error makes a measurement both. Which would you go with? Lock it in before the reveal. The correct answer is A. Reliable but not valid, showing that consistency does not guarantee accuracy. A is correct because the scale is reliable because it gives the same reading every time, but it is not valid because that reading is consistently wrong by 8 pounds. This is the course's classic illustration that a measurement can be reliable without being valid. B is wrong because the scale is highly consistent, so it is reliable, which rules out the valid but not reliable label. Its problem is accuracy, not consistency. C is wrong because a scale that is always 8 pounds off is not valid, because it does not accurately measure true weight. Consistency alone does not make a measurement valid. D is wrong because the scale is reliable because its error is perfectly consistent, so calling it neither reliable nor valid is wrong. The whole point is that reliability is present while validity is absent. Let's lock in the classic example that separates reliability from validity. the bathroom scale that always reads 8 pounds too heavy. The scale is reliable because it gives the same result on every weighing with no wild variation. Reliability only asks whether a measurement reproduces, and this one reproduces perfectly, even though its error is steady. But it isn't valid because it's supposed to measure true weight and it never does. Every reading is 8 pounds off. A measurement can repeat perfectly and still be invalid if it's wrong about the trait it claims to capture. A target with arrows makes this visual. Reliable but not valid is a tight cluster far from the bullseye. Valid but not reliable is scattered arrows centered on the bullseye. And reliable and valid together is a tight cluster right on it. The faulty scale is that first picture, tightly grouped in the wrong place. This is the most common trap in the topic. A steady, repeatable measurement can still be systematically wrong. Keep the 8 pounds too heavy scale in mind and you'll never confuse being reliable with being valid again. Question 39. Citing Raymond Pankow, the course gives approximate undetected error rates for human work. Which pairing of task type and error rate is correct? Your options are A. Simple mechanical tasks such as typing, about 5%. B. Simple mechanical tasks such as typing, about 0.5%, and complex logical tasks such as writing programs, about 5%. C. Complex logical tasks such as writing programs, about 0.5%. D. Both simple and complex tasks, about 50%. Don't overthink it. Which one feels right? The correct answer is B. Simple mechanical tasks such as typing, about 0.5%, and complex logical tasks such as writing programs, about 5%. B is correct because Pankow found that for simple mechanical tasks such as typing, people make undetected errors in about 0.5% of actions, while for complex logical activities such as writing programs, the rate rises to about 5%. The complex task rate is roughly 10 times the simple task rate. A is wrong because typing is a simple mechanical task with an error rate of about 0.5%, not 5%. The 5% figure belongs to complex logical work. C is wrong because writing programs is a complex logical task with an error rate of about 5%, not 0.5%. This option swaps the two figures. D is wrong because neither rate is anywhere near 50%. The course's figures are about 0.5% for mechanical tasks and about 5% for logical tasks. Human error in data isn't just possible, it's certain, and researcher Raymond Pankow put actual numbers on how often it happens. When people do simple mechanical work like typing, they make undetected errors about 0.5% of the time. When the work is complex and logical, like writing programs, that rate jumps to roughly 5%, about 10 times higher. The harder and more cognitively demanding a task is, the more often people make mistakes without even realizing it, because logical work involves judgment and many interacting decisions. This isn't about carelessness or poor training. Error is a predictable feature of human work, which is exactly why checking and structure aren't optional extras but necessary defenses. Keep these straight. Typing carries about 0.5% error rate, while writing programs carries about 5%, roughly 10 times more, since human error is one of the main ways bad data enters any system. Question 40. In a rectangular data file, one column holds every subject's age and another holds every subject's phone number, while a single row holds all of the collected information about subject A. Which statement correctly matches the terms to the structure? Your options are A. The age column is a record and subject A's row is a field. B. Both the columns and the rows are called fields. C. Both the columns and the rows are called records. D. The age column is a field and subject A's row is a record. Got a guess? Lock it in. The correct answer is D. The age column is a field and subject A's row is a record. D is correct because A field contains information about one part of each subject, such as age or phone number, and is typically represented by a column. A record contains all the data for one particular subject, such as everything about subject A, and is typically represented by a row. A is wrong because this reverses the terms. The column of ages is a field and subject A's row is a record, not the other way around. B is wrong because rows and columns are not both fields. Columns are fields and rows are records, so the two terms are not interchangeable. C is wrong because rows and columns are not both records. Rows are records and columns are fields, so collapsing them into one term is incorrect. Once data is organized into a spreadsheet, two terms describe its basic units, fields and records. They're easy to mix up, but their orientation in the grid tells you everything you need to know. A field contains information about one part of each subject, like an age or a phone number, recorded the same way for everyone. A record contains all the data for one particular subject, everything collected about that one person. Picture the data as a grid. The age column running down is a field holding the same attribute for every subject. The row for subject A running across is a record holding every attribute for just that one subject. Where they cross, you get a single value. The cleanest way to keep them straight is to anchor each term to its direction. Fields are columns holding one attribute. Records are rows holding one subject. This vocabulary underpins rectangular data files, the preferred way to store data, where fields as columns and records as rows make it easy to spot errors and analyze data. Question 41. A city government surveys its recent immigrant population entirely in English, and many people from non-English speaking countries do not respond, leaving that group underrepresented. According to the course, what kind of error is this and what is its typical effect? Your options are A. A row shift error, which leaves all subsequent records one row off. B. A software incompatibility error which corrupts data during translation. C. Missing data and omission error, which tends to skew the results of the analysis. D. A placebo effect, which biases the control group's responses. Which one is it? Pause the video if you need more time. The correct answer is C. Missing data and omission error, which tends to skew the results of the analysis. C is correct because missing data is an omission error, occurring when crucial data is absent. And the course uses this exact English-only survey example because non-English speakers are underrepresented in a patterned way tied to the variable of interest. The results are skewed, illustrating that missing data tends to skew analysis. A is wrong because a row shift error happens when a data entry person skips a row, misaligning later records. The survey problem is non-response, not misaligned data entry. B is wrong because software incompatibility corrupts data when moving between programs that do not translate correctly. The issue here is who responded, not a software conversion fault. D is wrong because the placebo effect occurs in the control group of a trial when participants believe they received treatment. It has nothing to do with survey non-response. Missing data, also called an omission error, is one of the most serious problems a data set can have. It happens when crucial information never gets collected, whether by accident, on purpose, or because of flaws in the study design itself. The core danger is simple. Missing data tends to skew results, pulling conclusions away from the truth. The analysis silently reflects only what's present, ignoring the gap where the missing data should be. Picture a city surveying immigrants about their national origins, but only in English. People who don't speak English can't respond, so they vanish from the data, and the results end up painting a distorted picture of the very population the government wanted to understand. The deepest lesson is that missingness is rarely neutral. When the reason people are missing connects directly to what's being studied, like native language predicting who skips an English-only survey, the skew becomes severe, because it's not random thinning but systematic silencing. So whenever a group central to a study fails to respond, that's the signature of the most damaging kind of missing data. Question 42. After collecting data, an analyst enters it into a spreadsheet or relational database so it sits neatly in rows and columns, making it easy to check for missing or out-of-range values and to port into packages like SPSS, SAS, and R. What is the course's name for files organized this way, and how does it regard them? Your options are A. Rectangular data files, which are the preferred method of storing data. B. Unstructured data files, which must be quantified before storage. C. Construct files, which operationalize abstract concepts. D. Cohort files, which follow subjects forward in time. Take a second. Which answer would you pick? The correct answer is A. Rectangular data files, which are the preferred method of storing data. A is correct because files organized into neat rows and columns are called rectangular data files, and the course names them the preferred method of storing data. Their rectangular structure is exactly what makes it easy to scan for missing or out-of-range values and to move data into statistical packages. B is wrong because unstructured data does not fit a row and column format and must be quantified before analysis, which is the opposite of a neat rectangular file. The scenario describes well-organized structured data. C is wrong because a construct is a quantifiable variable created by operationalizing an abstract concept, not a way of storing a data set. The term does not describe a file format. D is wrong because a cohort is a group of subjects observed over time in a study, not a file of rows and columns. The term belongs to research design, not data storage. Before data can be analyzed, it has to be organized, and that means putting it somewhere specific, a spreadsheet or a relational database. Data organized into neat rows and columns forms what's called a rectangular data file. Rows are records, columns are fields, and this uniform grid is the preferred way to store data because it can be scanned and checked in predictable ways. It's important to keep these separate. Spreadsheets and relational databases are where data is organized and stored. SPS, SAS, and R are statistical packages used only for analysis after the data has been ported in from storage. Because the grid is regular, it's easy to scan for missing values or out-of-range values. Spreadsheets are simpler but more error-prone, while relational databases handle larger, more complex, interrelated data more reliably. One set of tools keeps the data organized in rectangular form. The other set, the statistical packages, processes it afterward. Keeping that distinction clear is exactly what this topic tests. Question 43. A school district analyst takes students' exact SAT scores and groups them into broader high, medium, and low categories so the values are easier to work with. According to the course, which data management technique is this, and how does it differ from transforming data? Your options are A. It is transforming data, which means relabeling values into broader categories. B. It is handling missing data, which means filling in absent values. C. It is checking data, which means reviewing for out-of-range entries. D. It is recoding data, which reassigns or relabels values within a variable, whereas transforming changes data from one form into another. Before I reveal it, which one do you think is right? The correct answer is D. It is recoding data, which reassigns or relabels values within a variable, whereas transforming changes data from one form into another. D is correct because recoding reassigns or relabels values within a variable, and grouping exact SAT scores into high, medium, and low buckets is the course's own example of recoding. Transforming, by contrast, converts data from one form into another, such as quantifying unstructured text. So the two techniques are distinct. A is wrong because transforming changes data from one form into another, such as turning text into numbers, not grouping values into categories. Relabeling scores into buckets is recoding, so this option mislabels it. B is wrong because handling missing data deals with absent values, but the scores here are present and simply being grouped. No values are missing in this scenario. C is wrong because checking data means reviewing entries for errors or out-of-range values, not grouping scores into categories. The activity described is recoding, not error checking. Data management includes many techniques for preparing raw data, but two are especially easy to confuse: transforming data and recoding data. Both aim to produce clean, analyzable data, but they are fundamentally different operations. Transforming data means converting data from one form into another so it can be analyzed. The clearest example is quantifying unstructured data, turning text, images, or clickstreams into numbers, since unstructured material must be quantified before any analysis is possible. Transforming can also mean changing a field's format or units. Recoding data means reassigning or relabeling values within a variable rather than changing its form. One common use is collapsing a detailed variable into broader categories, and another is converting category labels into numeric codes. In both cases, the variable stays the same, only how its values are grouped or labeled changes. Consider the subject's own example. Exact college entrance exam scores get categorized into high, medium, and low segments. The scores aren't converted into a different kind of data. Each precise score is simply reassigned to a category. That's a relabeling of values within the score variable, which is exactly what recoding does. So the key check is this: did the operation change what kind of data it is, which signals transforming, or did it merely change how existing values are categorized, which signals recoding? Quantifying text is transforming. Bundling scores into high, medium, and low is recoding. Question 44. A team runs a highly sophisticated statistical analysis, but the data it starts with is riddled with errors and inaccuracies. According to the course, what does the GIGO principle predict about the results? Your options are: A. The sophistication of the analysis will correct the flawed input and yield reliable results. B. Flawed input data will produce questionable analyses because garbage produces garbage out. C. The flawed data becomes valid as long as the sample is large enough. D. The results will be reliable but not valid regardless of the input. What's your answer? Commit to one before I continue. The correct answer is B. Flawed input data will produce questionable analyses because garbage in produces garbage out. B is correct because GIGO, garbage in, garbage out, holds that starting with flawed data produces questionable analyses no matter how sophisticated the method. The course is explicit that accurate input yields reliable results while flawed input yields questionable ones, so the errors here will carry through to the output. 8 is wrong because GIGO directly contradicts this, since sophisticated analysis cannot rescue flawed input. A flawless analysis performed on garbage data still produces garbage conclusions. C is wrong because a large sample does not cleanse inaccurate data, and the course never claims size repairs flawed input. Volume of bad data does not make it valid. D is wrong because GIGO predicts questionable results from bad input, not a neat, reliable, but not valid outcome. That reliability and validity distinction is a separate idea from GIGO. GGO stands for garbage in, garbage out, a phrase borrowed from computer programming. It means the quality of an analysis is capped by the quality of the data that feeds it. No matter how sophisticated the statistical technique, if the input data is bad, the output will be bad. A flawless analysis run on garbage data still produces garbage conclusions, just dressed up to look trustworthy. GGO is the bridge connecting several ideas to actual results. It's why reliability and validity matter, why data cleaning is vital, why missing data is dangerous, and why research design matters, since each is a source of garbage in. Picture the same analysis process fed two different ways. Clean, accurate data in produces reliable results out, while flawed, garbage data in produces garbage conclusions out, even though the method itself never changed. That's why analysts sometimes spend more time cleaning data than analyzing it. Since output can never rise above input quality, ensuring accurate data isn't a distraction from the real work, it is the real work. Question 45. A data manager wants to reduce data entry errors and also make it easy to trace where any error originated. According to the course, which two safeguards directly serve these goals? Your options are A. Maximizing the sample size and randomizing the participants. B. Blinding the response gatherer and using a placebo. C. Checking the data repeatedly and setting up a hierarchical reporting structure where each person is responsible for a different aspect. D. Converting all interval data to ratio data and spelling out numbers. Pick one. Trust your gut. Here's your chance to test yourself. The correct answer is C. Checking the data repeatedly and setting up a hierarchical reporting structure where each person is responsible for a different aspect. C was correct because the course recommends checking the data, checking it again, and checking it one last time because time spent checking is time not spent reanalyzing. It also recommends a hierarchical reporting structure in which each person is responsible for a different aspect, which makes it far easier to determine where something went wrong. A is wrong because maximizing sample size and randomizing participants are research design choices, not safeguards against data entry errors. They do not help trace where an entry mistake originated. B is wrong because blinding and placebos control bias in experiments, not data entry mistakes. They do not address checking data or tracing errors. D is wrong because changing measurement levels and spelling out numbers are unrelated to catching entry errors or tracing their source. Neither is a data management safeguard the course recommends here. Human error in data entry is inevitable, so the real question is how to guard against it. The subject offers two concrete safeguards, repeated checking and a hierarchical reporting structure. Together, these defenses address the two things an organization most needs when mistakes will certainly occur: catching errors and tracing where they came from. The first safeguard is repeated checking. Check the data, check it again, and check it one last time. This triple repetition matters because a single pass isn't enough, and catching an error early is far cheaper than discovering it after wrong conclusions have already been drawn. The second safeguard is structural, a hierarchical reporting structure where each person is responsible for a different aspect of data management. When responsibilities are divided this way, an organization can isolate exactly where something went wrong instead of searching blindly. Repeated checking maximizes the chance of catching mistakes, while hierarchical structure minimizes the effort of tracing them. Used together, these two practices form a fuller defense against the certainty of human error. Question 46. A retail chain hires mystery shoppers whose identities are unknown to store staff, reasoning that if the staff knew they were being studied, their behavior would change. Which type of research design is this, and why is it chosen here? Your options are A. An observational study, because it is impossible to control the conditions without changing the staff's natural behavior. B. An experimental study, because the researcher fully controls and manipulates the staff's behavior. C. An experimental study, because a treatment is administered to the staff. D. A prospective cohort study, because the staff are followed backward through past records. Which would you go with? Lock it in before the reveal. The correct answer is A, an observational study, because it is impossible to control the conditions without changing the staff's natural behavior. A is correct because mystery shopping is the course's example of an observational or quasi-experimental study used because controlling the conditions is impossible. If staff knew about the study, their behavior would change. So the researcher can only observe natural behavior rather than control it. B is wrong because an experimental study requires the researcher to control and manipulate conditions. But here the whole point is that the staff's behavior cannot be controlled without ruining it. That impossibility makes the study observational. C is wrong because no treatment is administered to the staff. The mystery shopper simply observes. Without a manipulated treatment, this is not an experimental design. D is wrong because a prospective cohort study looks forward in time from enrollment, not backward through past records. The mystery shopping example is about observing natural behavior, not following a cohort. Research design splits into two main types: observational studies and experimental studies. The fundamental difference between them comes down to one thing: control. In an experimental study, the researcher controls conditions, including who gets which treatment. In an observational study, the researcher can't manipulate anything and simply watches what happens naturally. Take mystery shopping in retail. A shopper whose identity is unknown to staff quietly evaluates their service and reports back. If staff knew they were being studied, their behavior would change, so control is impossible, making this the perfect case for an observational design. The strongest observational studies are prospective, following a cohort forward in time from enrollment, rather than looking backward. This design trades weaker statistical proof of cause and effect for the powerful advantage of observing real, unconstrained behavior. Whenever a scenario turns on whether the researcher can control conditions, remember, control it. And it's experimental, only watch it, and it's observational. Question 47. A researcher wants to estimate support for a presidential candidate among all registered United States voters, but cannot survey everyone, so a smaller representative group is studied instead, chosen so that the selection of any one person is independent of the selection of any other. Which statement correctly applies the course's terms? Your options are: A. All registered voters are the sample, and the smaller group is the population. B. All registered voters are the population. The smaller group is a sample, and random selection requires that choices be independent. C. The smaller group should be drawn from a single homogeneous neighborhood to keep results consistent. D. The smaller group is a control group since it does not receive any treatment. Don't overthink it. Which one feels right? The correct answer is B. All registered voters are the population. The smaller group is a sample, and random selection requires that choices be independent. B is correct because the population is the entire pool of interest. Here, all registered United States voters, and a sample is a smaller representative subset studied because the whole population is impractical to survey. The course also states that for a sample to be truly random, the selection of any particular subject must be independent of the selection of any others. As wrong because this reverses the terms. The entire pool of registered voters is the population, and the smaller studied group is the sample. C is wrong because drawing from a single homogeneous neighborhood would skew the results, since the course warns that homogeneous groups cannot represent a diverse population. A random representative sample is required instead. D is wrong because a control group is a concept from experiments, defined as the group that does not receive the treatment. This polling scenario involves sampling, not a treatment and control experiment. Every statistical experiment starts by deciding who or what to measure, which means understanding two key ideas: populations and samples, and how treatment and control groups reveal true effects. A population is the entire group of interest, like every American voter, while a sample is the smallest subset actually studied, because measuring the whole population is usually impractical. For the sample to stand in for the population, it must be chosen randomly, not from a narrow, homogeneous slice that would skew results. True randomness requires independence. Selecting one person must not change the odds of selecting anyone else. This is what stops hidden patterns from sneaking in and biasing the sample, giving it real representative power. After sampling, experiments introduce a treatment. The manipulation applied to subjects, given to a treatment group. A control group receives no treatment and serves as the baseline, showing what would have happened without it. Without a control group, there'd be no way to know if change came from the treatment or something else. The difference between treatment and control groups is exactly what the treatment actually caused. Question 48. A researcher setting up an experiment lists its 3 required elements as the subjects under observation, the procedures applied to them, and the effects those procedures produce. Which option correctly names these 3 elements in that order? Your options are A. Population, sample, and hypothesis. B. Construct, content, and statistical validity. C. Treatment allocator, participant, and response gatherer. D. Experimental units, treatments, and responses. Got a guess? Lock it in! The correct answer is D. Experimental units, treatments, and responses. D is correct because the course names the 3 elements of an experiment as experimental units. The subjects or objects under observation, treatments, the procedures applied to each subject, and responses, the effects of the experimental treatments. The scenario describes these 3 in exactly that order. A is wrong because population, sample, and hypothesis are concepts involved in setting up an experiment, but they are not the named 3 elements. The 3 elements are units, treatments, and responses. B is wrong because construct, content, and statistical validity are 3 of the 4 types of validity, not the elements of an experiment. They concern how trustworthy a study is, not its structural parts. C is wrong because treatment allocator, participant, and response gatherer are the 3 populations in a drug trial. Used to explain blinding? They are not the 3 elements of an experiment. Every experimental study, no matter the subject, is built from 3 core elements. Naming all 3 reveals the underlying structure of any experiment. Experimental units are the subjects or objects being studied. Treatments are the procedures applied to them. Responses are the effects those treatments produce, and the logic flows naturally from units to treatments to responses. These 3 elements are easy to confuse with a different trio: the treatment allocator, the participant, and the response gatherer. That second trio describes the people running a drug trial and is used to explain blinding, not the structure of the experiment itself. Alongside experimental structure, 4 types of validity ask whether a study's conclusions can be trusted: construct, content, internal, and statistical validity. Construct validity asks whether a construct is generally accepted in the field, while content validity asks whether it measures what it claims, being neither too wide nor too narrow. Internal validity guards against bias in the data, and statistical validity checks whether results hold up under hypothesis testing. A construct is simply an abstract idea, like intelligence or satisfaction, turned into something measurable. Keep the three elements straight. And remember, construct is about acceptance, while content is about fit. Tsaksu, that pairing is the classic trap. Question 49. A pharmaceutical researcher worries that the participants, the person assigning subjects to groups, and the person recording outcomes could all unconsciously bias a drug trial. Which design eliminates bias from everyone involved? And what is the placebo effect that makes blinding participants necessary? Your options are A. A triple-blind study in which participant, treatment allocator, and response gatherer are all unaware, while the placebo effect occurs when a control group participant shows treatment effects because they believe they are in the treatment group. B. A blind study in which only the response gatherer is unaware, while the placebo effect occurs when the treatment is administered incorrectly. C. A double-blind study in which no one, including the data analyst, is ever unaware, while the placebo effect occurs when a drug has no active ingredient. D. An observational study in which no groups exist, while the placebo effect occurs when staff change their behavior under observation. Which one is it? Pause the video if you need more time. The correct answer is A. A triple-blind study in which participant, treatment allocator, and response gatherer are all unaware, while the placebo effect occurs when a control group participant shows treatment effects because they believe they are in the treatment group. A is correct because a triple-blind study keeps the participant, the treatment allocator, and the response gatherer all unaware of group assignments, which the course says completely eliminates bias from anyone involved. The placebo effect occurs when a participant in the control group begins to show the effects of treatment because they believe they are in the treatment group, which is why blinding participants matters. B is wrong because a blind study keeps the participants unaware, not just the response gatherer, and it is the least rather than most thorough level. The placebo effect is about participant belief, not incorrect administration of a treatment. C is wrong because a double-blind study keeps the treatment allocator and participant unaware, but it is triple-blind that adds the response gatherer. The placebo effect is defined by belief in being treated, not by a drug lacking an active ingredient. D is wrong because an observational study still involves observation rather than controlled groups and is not the design that eliminates trial bias. The placebo effect concerns control group belief, not staff behavior under observation. Even with random samples, bias can creep into an experiment through the people running it, not just the people in it. Drug trials show both the problem and the solution. A drug trial involves three populations: the treatment allocator who assigns groups, the participant who receives treatment or placebo, and the response gatherer who records results. If any of them knows who is in which group, bias can slip in, even unconsciously. This matters because of the placebo effect. A control group participant may show improvement simply because they believe they're receiving treatment. That's why blinding the participant is essential to a clean comparison. Each level of blinding conceals the assignment from one more population. Blind hides it from the participant. Double blind adds the treatment allocator, and triple blind adds the response gatherer too. When all three populations are kept unaware, no one's knowledge can skew the results. That's why triple blind is the design that eliminates bias entirely. Question 50. An email marketing team finds that a deep discount subject line produced the highest open rate, click-through rate, and conversion rate, so they conclude it is clearly the best campaign for a company whose real goal is sales revenue. According to the course's Comfy Tech case, what is the key flaw in this conclusion? Your options are: A. The team should have used a larger font in the email subject line to raise conversions further. B. Conversion rate is irrelevant and only open rate should ever be used to judge a campaign. C. The team measured engagement and conversion rate but never compared how much each group actually spent. So, a lower converting campaign with a higher average order value could deliver more revenue and higher return on investment. D. The discount campaign failed because it produced the lowest click-through rate of the three. Take a second, which answer would you pick? The correct answer is C. The team measured engagement and conversion rate but never compared how much each group actually spent. So a lower converting campaign with a higher average order value could deliver more revenue and higher return on investment. C is correct because the Comfy Tech case shows the team measured lift in engagement and conversion rate but never checked which group spent the most. The metric aligned with the revenue goal. The course's example proves a campaign converting at 1% with a $250 average order value beats one converting at 2.5% with a $50 order value, giving the lower converting campaign the higher return on investment. A is wrong because the flaw is choosing the wrong success metric, not a design detail like font size. The course never suggests font changes as the issue. B is wrong because conversion rate is not irrelevant and open rate alone is also a vanity metric. The lesson is to combine conversion rate with average order value to judge return on investment, not to rely on open rate. D is wrong because the discount subject line actually produced the highest click-through rate, not the lowest. So this misstates the facts. Its weakness was attracting bargain hunters who spend little, not poor click-through. The Comfy Tech case study centers on one costly mistake, choosing the wrong metric to judge success. A footwear retailer's discount email won on open rate, click-through rate, and conversion rate, so the team called it the best campaign. That conclusion felt obvious and it was wrong. The flaw was that the test measured engagement and conversion rate but never measured what the company actually cared about: sales revenue. Opens, clicks, and conversion percentage made the discount email look effective at driving traffic, but they never revealed which group actually spent the most money. Suppose one offer converts at 2.5% with a $50 average order value, and another converts at just 1%, but with a $250 average order value. Per 100 recipients, the lower converting offer actually generates twice the revenue, revealing the true return on investment. This is the conversion rate trap. Bargain hunters convert often but spend little, while loyal buyers convert less often but spend far more. The case also warns against confirmation bias, since the team dismissed a colleague's hunch instead of testing it against real spending data. The central lesson of Comfy Tech is simple. Measure the metric that aligns with the real business goal. When the goal is revenue, conversion rate alone isn't enough. You need it paired with average order value to see the true return. That wraps up our C207 Domain 1 Q&A session for today. If you'd like more questions to practice everything we just covered, head over to our website. You'll find the link right in the description. It's packed with hundreds of free practice questions and complete study guides all ready and waiting for you to dive in. Subscribe to catch the next part, and good luck on your exam.